So welcome back. We're going to do an application with slope. We're going to look at slope as a rate. Now we talked about rates a little bit, and in our world, some rates that you may be familiar with is like driving a car. You have to drive so many miles per hour. So like the speed limit is 35 miles per hour. That would be considered a rate. Also, we have something like buying gasoline. A lot of times you'll buy so many gallons, so many gallons per dollar, or actually so many dollars per gallon, I guess you would say. You know, a lot of times gasoline is priced at so many dollars per gallon. I think today I saw it's $1.50 per gallon. Again, we're in this is 2016, so you know, compared to last year, this time prices are actually rather good. Now, taking rate into the form of slope, remember slope has this concept of linear in it. Work with lines, work with these linear concepts, work with lines. And so we have these vertical axes and these horizontal axes. You know, typically in our algebra, we've been just working with x and y. But in the real world, that horizontal axis is going to be defined as something, and that vertical axis is going to be defined as something. So, for instance, the horizontal axis could be hours, and the vertical axis could be miles. Therefore, the slope or the rate would be miles per hour. If the horizontal axis is in days and the vertical axis is in dollars, then the rate or slope would be considered dollars per day. So anytime it's written like that, that is kind of slope language, but also that's kind of our rate language. You know, dollars per day. You know, some of us may work dollars per day, so that's our rate of pay. Our example that is given to us is something about carbon dioxide, or what we call CO2. So worldwide carbon dioxide, in other words, CO2 emissions, they have increased from 14 billion tons in 1970 to 24 billion tons in 1995. This is from the World Resource Institute. Again, these days, you know, carbon is a big concept. We're trying to reduce what we call our carbon footprint. You know, trying to drive less, try to use less fossil fuels. So this is kind of an important concept. And it is tracked. You know, people are trying to record this information accurately. Now, for our purposes at this point, we're just going to start out at a little more smaller level. We're just going to try to find the slope-intercept form of the line. So using this information, we're going to try to find the slope-intercept form of the line. So we've got our axes. Notice that the horizontal axis is going to be our years, and our vertical axis is going to be the CO2 emissions. Notice that we didn't actually start at 0. Our origin actually started at 1970. So we can create any kind of scale we want. So I started at 1970. Looks like we're going to count by fives. 1970, 75, 80, 85, 1990, 1995, and then the year 2000. Now, you don't actually have to start exactly. You can actually make a little squiggly line here that says you're going to have a break in your graph. I'm actually going to just start at 14, and then I'm going to make my scale go from 14. So 14, 16, 18, 20, 22, 24, 26. So I kind of made this little jagged line to say, ignore this part. Let's start at 14, at that spot. So 14 billion tons in 1970. So in 1970, 14 billion tons could be identified at that spot there, 1970 and 14 billion tons. And then there's 24 billion tons in 1995. So if I go out to 1995, I can go up to 24 billion tons. So I can go up to that spot. Now what I could do is sketch out a line and say that this is actually going to be a linear concept. Let's say it's linear. We would have some type of graph like this. So there would be my sketch. What I want to do in our problem is we want to write an equation for this line. Now, remember, slope-intercept form is y equals mx plus b, where m is the slope and b is the y-intercept. It's pretty clear that it crosses at 14. So right now, I can pick up that b is equal to 14. Now, to determine my slope, though, I need to find my rise and run. So we know that this is 0, 14, and this was, actually, that was 1970, 14 for us. That's actually going to be our, that's an interesting thought here, since we started in 1970. That's going to be actually our 0 year. So 1970 is actually going to be considered our 0 year in our problem. And then we have 1995, and that's going to go to 24 billion tons. So what we do is find our change in y and change in x. So if it went from 14 up to 24, that looks like that's a count of a change of 10. So 2, 4, 6, 8, 10. And then it has to run over to that spot. So that's from 1970 to 1995. That looks like a, what, a 25-year span? From 70 to 95. So it looks like my slope is going to be 10 over 25, which would be, I can reduce that down, I can take a 5 out and make it, what, 2/5? So I can write this as y equals then 2/5 x plus 14. That could be my linear equation for this. Okay. So there is our slope-intercept form of our equation. And again, I could find slope by even using the slope form if I wanted to. y2 minus y1, 24 minus 14 would have gave me my 10. And 1995 minus 1970 would have gave me my 25. That would have given me my change that way. So there's my equation. Now, we also could look at this as y equals 0.4 x plus 14. In other words, I could say, find some spot here. I could change that 2/5 to a decimal and change it to a 0.4. And what that could mean is 14 billion or 0.4 billion per 1 year. What I can do is show that as a unit rate. So what I pick up on is, instead of saying 2 billion every 5 years, I could change that to a unit rate that says 0.4 billion per year. 0.4 billion per year. So, a couple ways to express our slope. We can express it as a fraction, or we can actually even express it as what we call a unit rate. So, predict the amount of worldwide emissions in 2005. Well, right now we know that in 1995 it's at 24 billion. And what we're picking up on is it's increasing by 0.4 billion per year. So from 1995 to 2005, that would be 10 more years. So in 1995, we know that there was 24 billion. And we also know that it's going to change at this rate of 0.4 billion per year. And if 10 years goes by, if I multiply that out, that's going to give me an increase of 4 billion. So it looks like in 2005, I'm going to have 28 billion altogether. Now we could also probably have put the 2005 into our formula, and it may have actually calculated it out for us. Because we're saying our y would be our emissions for whatever year we pick. So if I pick up a calculator, well, don't have a calculator, so if I type that in, y equals 0.4 times, and again, if this is the 0 year, 2005 would be, that's what, 30 years, that'd be like 35 years. Plus then 14. I think I'm going to actually change that back to 2/5. I think I can do 2/5 a little bit better. So notice that 5 goes into 35 7 times. 2 times 7 is 14. 14 plus 14 would indeed give me a 28. So actually I can use this as a formula to predict emissions. Some tricky things though is I got to remember that this is year 0. 1970 is my starting year. So only 35 years have elapsed, so that 35 would have to be the value there that I have to use. So there are some things we have to think about as we do that. But I actually could have used this as a formula to get the answer. And again, I kind of had to cheat because I did have a calculator, and I'm better with fractions in this case, because I could see that 5 would divide into 35 evenly. So there's some food for thought. Slope is not isolated to just x's and y's, but we could think of it in terms of the horizontal axis and the vertical axis, and those axes can be defined in very useful relationships. So I believe that's our only application at this point, and we're going to move back into some just pure algebra stuff. Stay tuned.